In this video, we're going to look at something called the equilibrium constant. Now, we had a constant when we were doing kinetics, the rate constant, but I got to be honest with you, the equilibrium constant is way cooler. It's way more useful. In kinetics, we just wanted to prove that the constant was constant for different trials of data. The equilibrium constant can be used to predict, number one, if a system is in equilibrium, and number two, if it's not at equilibrium, in which direction do we need to shift in order to get the reaction to a state of equilibrium? This is good stuff. And it's so easy. It's like an insult to your intelligence. It really looks like this. So you're going to have K equals. Whenever you have something in brackets that represents the molarity or the concentration, moles per liter, it's always going to be products over reactants. Let's write that in. Products over reactants. So you're going to start with your products. You're going to take the concentration of C and you just raise it to the power of the coefficient from the balanced equation. Now they picked kind of goofy symbols to use here. So our reactants and products are A, B, C, D. And our coefficients are like J, K, L, M. I don't know why they picked that. That's weird to me. But it is. So we're going to take our products and raise them to the coefficient in the balanced equation. Different than kinetics. In kinetics, those little exponents did not come from the balanced equation. Those had to be determined experimentally. We called them reaction orders. And it showed us how changing the concentration would affect the reaction rate. This is different. I mean, this is way easier. You take your reactants then on the bottom, and you just raise them to the ratio in the balanced equation. Now, at the time, everybody crushed kinetics. Everybody dominated kinetics, and it was relatively easy, hopefully, to figure out the orders of the reaction. You know, if it was first order, we double the concentration and we double the rate. And now, while we're in the midst of chapter 13, everybody's going to dominate equilibrium constants. They're super easy. Products over reactants. Take the concentration of your products, raise them to the power of the ratio in the balanced equation, the coefficients. Products over the reactants. I do the same thing with the reactants. The concentrations raised to the power of the coefficient in the balanced equation. Everybody crushes chapter 12 at the time. Everybody crushes chapter 13 at the time. Here's where it falls apart. When we get to the end of the year and we start reviewing for the AP test, then people get a little confused. In kinetics, when you had something that looked like this, R equals K, and let's say it was like, I don't know, A to the first and B to the second or something like that. These guys, these orders, reaction, orders, they must come from experimentation. They must come from experimental data. Must come from experimental data. They do not come from the balanced equation. Not in kinetics. In kinetics, those orders have to come from looking at experimental data. If I change the concentration of A, how does that affect the rate? This equilibrium setup looks so similar. You've got the concentration of your reactants and your products, and it's got these little exponents, but now the exponents are from the balanced equation. This is so much easier. You don't need any kind of data. So for example, if I wanted to write the equilibrium expression, I'd say K equals the expression for the equilibrium constant. Products, so I've got this NO2, and I'm going to raise it to the fourth power. Gosh, that's easy. My other product is water going to the sixth. Products over reactants. NH3 to the 4th, ammonia, and oxygen to the 7th. That's all there is to it. So I have no doubt that right now you're going to dominate equilibrium constants. Or sometimes they might just say, like, write the equilibrium expression for this reaction. But just know in the back of your mind that when we get to the end of the year and we start putting this all together, kinetics is a little different. Even though you see like some similarities between the two setups, in kinetics those exponents must come from experimental data. Okay, so you are going to love equilibrium. Watch what we can do. We can calculate the constant. So we have the following reaction for the Haber process, which is the formation of ammonia. Nitrogen reacts with hydrogen to form ammonia. Equilibrium constants do depend on temperature, so they'll usually specify, like, at a particular temperature what is the constant, especially since a lot of these reactions do have an energy component. They don't always write it in. The position of the equilibrium could change depending on the temperature of the reaction. Not that this is going to affect our calculations, but just note that they will usually specify a temperature. We want to calculate the value of K. And so now they're going to give us concentrations, which, I mean, these are numbers that actually really aren't that crazy. They put them in scientific notation, but maybe just to make things look a little simpler, would it be okay if I put this as 0.031 molar, like moles per liter, or like 0.85? And how about we say this is, ooh, that one's small, 0.0031, something like that. Let's use those numbers. I mean, they're the same numbers, obviously, but our setup will just look a little simpler. Okay, so all we do now is set up the equilibrium constants expression, and then we sub in the numbers and solve for K. So easy. So let's go K equals products over reactants. My product is the ammonia to the 2nd over reactants. Nitrogen to the 1st and H2 hydrogen to the 3rd. Plug and chug, that's all there is to it. I love this stuff. Products, ammonia, 0.031 squared over reactants, 0.85 to the 1st and 0.0031 to the 3rd. So we plug this in our calculator. Let's say 3.8 times 10 to the 4th. There's K. That's it. Do you think you can handle this? I think you might even kind of like this, even though you don't want to admit it. Okay, so let's do the same thing. But now watch what we're going to do with the system. What if we flip it? What if we flip this thing? So now my setup is flipped. If I go products, now it's the nitrogen to the 1st and the hydrogen to the 3rd over reactants, the ammonia squared. Okay, so we're just going to plug in, but it's actually just going to be the inverse of what I just did. So let's say my products, 0.85 is my nitrogen to the 1st, my hydrogen, 0.031 to the 3rd, and then on the bottom now I have my ammonia, 0.031 to the 2nd. So now let's plug this in our calculator. We'll leave like 2 sig figs and say 2.6 times 10 to the -5th. Gosh, this is so easy, isn't it? Okay, let's try one other option. Let's do this. Let's get nuts and change the ratio. So now I got K equals products over reactants. We're going back to the original. We're going to form ammonia. I just changed the ratio. So now we're going to make 1 mole of ammonia. So that's going to be to the first, which obviously you don't have to write into the first. Then I'm going to have nitrogen to the 1/2. Or I guess you could kind of say like the square root. And then I'm going to have hydrogen to the 3/2 power. And then we just plug in. So it's going to look the exact same thing as A, 0.031. My exponents are just a little different. 0.85. Now you are going to the 1/2, or we're going to take the square root, and 0.0031 to the 3/2 power. Excellent. All right, so let's plug this in our calculator. Okay, I haven't hit these buttons for a little while. This is fun. I'm going to say, ooh. Okay, I'm just going to say 195. I'll say 195. Okay, check this out. We had the same reaction, but we just somehow kind of altered that reaction. Do you see what I see? I bet you do. Like, you might have caught on to what we did here. So originally we set this up and solved for K. Let's call this K. This is K. That's a weird looking K. There. So that was the original equation. Most of the time that's the way we see this Haber process set up for the formation of ammonia. Look what happens in the second one. In the second one, I flipped the equation. So we flipped our products and reactants, which really just means that we kind of like flipped our equilibrium expression. Do you see how that changed the value of K? If our equilibrium expression was flipped, so basically it was like the inverse. Do you see that this is like just 1 over K? If I took 1 over 3.8 times 10 to the 4th, I get about 2.6 times 10 to the negative 5th. Oh, now this is something they could do on a multiple choice question. Excellent. So they might say, hey, the value of the constant is blah, and maybe they would give you some manageable number. How would the constant change if this were reversed? And you don't really have to like do the entire setup. You don't have to do the whole calculation, although we did here and it was fun. If you recognize like, oh, well, if we just invert the equation, we invert the equilibrium expression, we're going to invert the value of K. So obviously they would give you numbers that are manageable, that you could do this without a calculator, but you know, maybe they said K is 10. Okay, so then if I do something like B, it would just be 1 over 10. I could do that without a calculator. Or now notice C. Compare A and C. So now the equations are going in the same order, products over reactants, they're the same setup, but we changed the ratio, we halved the ratio. Well, when I look at my equilibrium setup, the ratio from the balanced equation becomes the exponent. So if I halved all the exponents, do you see that it's kind of like then taking your original K, but going to the 1/2 power? Which is really like taking the square root of K. So again, if they did this multiple choice, you wouldn't have to plug everything in your calculator if you recognize the relationship between these K values. So we've got the straight up equation in part A. In part B, if you invert the reaction, you invert your equilibrium expression, you just invert K. You can just take 1 over the original K value. Or in part C, if I do something like I half the ratio from the balanced equation, it's like taking K to the 1/2 power, which is kind of like the square root of K. That would be something they could have you solve for on a multiple choice style question. Obviously, they wouldn't have you like solve for the values of K like we did here if it were multiple choice. You probably want a calculator for that. But we could compare different K values if we recognize the relationship between the original equation and the new equation.